Hi, good evening, everybody. Let me share my screen. Hope my screen is visible.
Yes, sir.
Right. So, actually, uh, we are entered into the quiz 2. Maybe end of that 8 weeks of course. We are going to face and you are going to write the quiz 2 examination. Maybe it's coming Monday. There are 2 revision sessions we actually plan. Uh, week 5 and 6 is a one revision session, and week 7 and 8 is another revision session, because the week 5 and 6 and 7 and 8 it contains the complex concepts. So that number of questions also we need to discuss more. That's the reason today is the week 5 and 6, and that coming Friday is the 7 and 8. So that is the thing. During this revision session, we'll try to solve some of the previous questions, which are some standard questions are there. I will discuss that questions along with your mock. Already mock quiz 2 is released. That questions also I'll discuss. The questions that belongs to week 5 and 6. While solving the question, we'll discuss what is the concept, how we are solving, the approach of solving, basically the concept behind it, how to solve it. So that's a way I planned today. Shall I proceed? Yeah, cool. Yes.
Yes, sir.
Yeah. So let me start that some of previous year standard questions, which are standard patterns, which you can find it. Some questions which belongs to the week 5, some questions belongs to the week 6. If we completely simply just we want to look at what concepts are there in the week 5 and 6. So week 5 is, yeah. So week 5 is completely, this could be the back. So the week 5 is my screen visible? What I'm writing?
Yeah, it's visible.
Yes, sir.
Yes, sir.
Week 5 is completely the weighted graphs. So whenever weighted graphs are available, there are standard algorithms are there, like shortest path. We are saying it a single source shortest path, where it is Dijkstra's algorithm, Dijkstra's one, which is a single source one, and we have another algorithm called Bellman-Ford. Bellman-Ford. This is also single source shortest path. These two are that single source shortest path. And when it comes to that, Floyd-Warshall, it is multi-source shortest path, MSSP, like short form I'm using. So after that, there is spanning trees concept is there, where the spanning tree algorithms are two. One is Prim's algorithm, and the next one is that Kruskal's algorithm. So mostly these are the standard questions we are getting from the week 5. And when it comes to the week 6, week 6, the concept it belongs to the week 6 is that. So that is completely trees. Of course, most possibly we are using it as a binary trees. Along with the binary trees, maybe heaps are there, some concepts on the heaps, max heap and min heap. That is some interesting questions on the heaps. So these two concepts, following these two concepts and two standard algorithms, some of them, we try to go that each question and we try to understand what is the concept behind it, how to solve it. So let me jump into that. While I'm solving, maybe I'll jump between this my document and as well as your mock quiz paper. Let me open my mock quiz. I did not open it. Yes. Hope everyone is able to access this mock quiz too. Right?
Yes, sir.
Great. Sometimes similar concept is there, means I'll come to the mock quiz also, and I'll go to that some of standard questions also. So now let's see this question. So consider there is a directed graph on which the Dijkstra's algorithm we are using, which run that with vertex P as a source vertex. So we are using this vertex P. This P is a source. We are using this is the source. And what is the order of the nodes, which the nodes are marked as visited by Dijkstra's algorithm? See, Dijkstra's algorithm, as you know that, as and when the source vertex is fixed, immediately it will set that particular path distance is that source is 0. The rest of them are infinite. Am I right or wrong? Is it right?
Yes, sir.
Rest of them are infinite, no?
Yes, sir.
Yeah.
So then it starts traversing. So like from source vertex to what is that lowest distance or lowest cast, lowest weight edge
Q.
is there, that allow. Yeah. So this P source is fixed. We try to traverse that shortest path of order, like P to all of the vertices, single source. The source is already fixed. We are trying to find out the shortest path using that Dijkstra's algorithm. Standard algorithm is Dijkstra's, they said it. So whenever Dijkstra's is there, we try to have that all of them are infinite except the source. Now, the thing is, the question they are asking is, what is the order of nodes? Like which particular sequence of order of nodes are going to be visited? So as you know that, whenever that you can say that the Dijkstra's algorithm or any other, shortest path algorithms, there is a visited matrix is there. Maybe, visited dictionary, what you can call us. So initially all of them, it contains that maybe it is, false. All of them. Maybe, all of them. So this, all of them are false. Out of that, which one is traversed first and what is next, what is next? But here there is a note was given. See, look at here. If two vertices have same distance, then the algorithm picks that next vertex with first alphabetically, chronological order. For example, the distance from P to Q and P to U is same. What it will do is, whenever it's same, then it will do that whichever same is that, then alphabetically whichever the first, that's going to be selected. That's what, the sequentially it happens alphabetically. If it is A and B is there, both of them are having the edge weights of 5 and 5, A is going to be selected. That question, hope you understand. Is it right? Hope you understand, no?
Yes.
Fine. So now let's do that. Let's do that, the Dijkstra's algorithm, how we are solving it. So look at here, P2Q and
Sir,
P2S. Hello. Hello.
screen little bit zoom
Okay,
out.
still zoom it. Is it okay? Is it okay now?
Yes, sir, a screen zoom out.
Hello.
Yes, sir.
Yes, sir, okay.
Okay, fine. So now from the P, we are trying to traverse towards Q side or U side is what is the shortest distance is 5, so that this infinite will go, 5 will be updated. So whenever visited sequence, if you take it, because they asked you the visited sequence, the first visited one is definitely P. Then out of the Q and U, so whatever the lesser distance is there, it is Q. So that definitely next visited is Q. Am I right?
Yeah.
Then
Yes, sir.
after it, from the P, another adjacent vertex is there. That distance also updated. It's going to be 8, because that is. But whenever you come to that from the Q, there is a distance of that R, which is already 5 plus 6. It's 11 is there. No way. 5 and this particular Q to S is having 8. 8 is there, no? Is it right? From the Q
Yes.
to S, there is
Yes,
a
sir.
8, and from the P, there is a 8. Hope you understand. These two, this is also 8. Whenever it comes to here, this is also 8. Is it right?
Yes, sir.
Yes, sir.
But whenever P to U, there is a 8, and P to S, there is a 8, which one you choose it? Because based
Yes.
on the note, you need to follow. Because alphabetically, S is before the U. So that we definitely select that S. here is that alphabetical order will come. So once S is over, there is no other choice. S is over means, will you select R? Means definitely no, because R is having 5 plus 6, 11 distance. So we don't select the 11. We don't select 11, no? Is it right? Here it's
Yes.
11, 11 is updated. We don't select 11. So here is, this is the best choice because 8 is the best choice. Even you compare that 8 plus 5, 13, this is also not best choice. So that we definitely select that U is the next. After U is over, P is over, Q is over, S is over, then R is there and T is there. R is having two ways, like 5 and 6, 11 is there, and 8 plus 4, 12 is there, but 11 is going to be updated because it's the shortest way to reach that from P to R. And similar way, to reach the T, there is 8 plus 6, 14 is there. There is 8 plus 5, it's a 13 is there. 13 is taking as a final value. Out of this R and T, which one you choose it?
R.
So we choose R. So that R is going to be there. The last one is that ultimate one, it's a T. So simply, whatever graph is given, you try to put the infinite and starting vertex is 0. So rest of them optimized values you calculate manually, just simply putting that, and you can get the answer. Wherever similar weights are there, we try to choose that alphabetically, whichever first, that is going to be chosen. So hope you understand.
Yes, sir.
Now the situation is, hello. Somebody has to mute kindly. That makes it interesting. So let me see that any mock question is there on the Dijkstra's algorithm. So this is not Dijkstra's one. I think it's a minimum cost spanning tree. We don't consider this. So here is one more. Please look at here. There is a question number 2 in the mock. So the question number 2, which is, they are asking that, suppose we want to find out the shortest path from the source vertex of S to other nodes. So definitely it's a single source shortest path. Is it right? Because S is, they are fixed as a source, no? This is a fixed as source. This is a source. Let me check the color. Let me take it. This is a source. Is it right? Is it right?
Yes.
Yes.
Now this question it contains that, what it contains is, they are giving that Dijkstra's algorithm, Bellman-Ford also, they are asking whatever it is, how really it works. Just before just directly going for this question, just let me understand you. The Dijkstra's algorithm works with graph with no negative weights. Please remember, it's a direct theoretical rule. No negative weights. It's a standard rule. It's a standard rule. But it does not mean that some specific graphs are there. Even negative weights are also there, it works. That's what we need to think about it. But this statement is a general statement. As per the algorithm definition, just you can check the mathematician who have defined that Dijkstra's. The graph with positive weights only Dijkstra's will work. So then, what is the use of this Bellman-Ford is? The Bellman-Ford, it works graph with negative weights, but no negative cycles. But no negative cycles. So these two statements you need to remember. I will tell you what exactly, negative weight and negative cycle. So let me show you that. Here there is a graph. So we are having this a part of a graph, or we can say that a subgraph of a graph. So this is a graph which is available. So in this 2, -2, and 3. So in this case, what happened? Negative weight is there, but there is no negative cycle. How can you say is initially what you have is 0. Here it is infinite. Here it is infinite. Am I right or wrong? Is it
Yes,
right?
sir.
So now this is updated with 2. Then 2 minus 2, it will become 0. Is it right? 0.
Yes, sir.
So then after that, 0 to 3, if you consider, it's going to be 3. Does 3 is smaller or 0 is smaller? 0 only smaller? No, 0 is going to be finalized. Is it right? Because minimum value you're taking. Is it right?
Yes, sir.
Yes, sir.
So that the values are stabilized. What you can say that the values are stabilized. The values are stabilized. So it means that no negative cycle. No negative cycle. Negative weights are there, but negative cycle is not there. Now let us take another graph. I'm taking another graph. So
So can you
same
please
that
explain the determination of a negative cycle again?
So if you run it that particular Dijkstra's algorithm, or it could be that Bellman-Ford, once the particular traversal is over, like single source shortest path is over, again if you rerun also same values will come. Is it right?
Yeah.
First time, second time, n number of iterations we run it, no? So n
Yeah.
number of iterations you run it also, same particular values are stabilized. For example, I'm taking another graph. Same graph I'm taking. But here, what I did is 2, -3, and -1. So remember, here we are putting it is 0. Basically, these are infinite, these are infinite. Let me run first time, because we are running that Bellman-Ford, because Bellman-Ford, it tries to work out that negative weights, but negative cycles are reported. So negative edge weights it works, but negative cycles it doesn't work. Now what happened? 0 to this one is updated with infinite is going to be 2. Then 2 to -3 is going to be -1. So -1 and -2 will become -2, because -2 is smaller than 0. No, is it right?
Yes, sir.
Yes.
Again one more edge relaxation. Again one more time, if you run it, what happens? -2 will become 0. Is it right? 0 -3, it will become -3. So -3 and -2, it will become -4. See that the values are not stabilized. Not stabilized. That can be identified by Bellman-Ford. This is basically in the theoretical thing we have explained you that what is the negative edge and negative edge cycle. Is it right?
Okay, so in the second example, while we were doing the second round, we saw that the numbers were going down. They were going negative only. So that is what we
They are
see a
not
negative cycle.
stabilized forever.
Okay.
Okay. So
So if it's
now,
going negative continually, then it means it's a negative cycle.
yes, the negatives are continuously going down and down. Okay.
Okay. Okay. Got it. Thank you, sir.
So now this graph they have given, please look at this graph. Now please identify whether negative cycle is there, negative edge weights are there. Please look at it. So now let me open this. Any part. So because source is already fixed, because already they said it is source is this particular one is source. So this is source. Is it right? Because S is source, no?
Yes, sir.
Can you tell me any negative cycle is there? Started from a particular vertex, again ended with same vertex. No.
No,
So
sir.
here, negative edge weights are there, negative cycles are not there. Now what happened? Your Dijkstra's algorithm works at this time, because the Dijkstra's algorithm general statement they said it, Dijkstra's algorithm not suitable for the graph with negative weights, but sometimes it is suitable because it doesn't know. If you run it, so first time itself you will get the value, second time if you run it also same values will get it, So this works that in this graph, so Dijkstra's will work. Dijkstra's will work. Work. Even negative weights are there, but generally it doesn't work, because as per the mathematician, when he was developed the algorithm, he thought that this algorithm is not suitable for negative weights, but some specific graphs are there. These kind of graph, for example, if this particular cycle is like this, what the cycle is, if this arrow is reversed, then what happens, negative cycle it goes. Is it right?
Right, sir.
Yes.
So at that time, the
Yes,
Dijkstra
sir.
doesn't work. Bellman-Ford will report that there is a negative edge cycle is that, please take care of it. But Dijkstra's algorithm doesn't report, but Bellman-Ford it will report. So there is a negative cycle is that, please take care of it. So now let us see the options. What options they have given. Fine. So this particular graph, which of the following, the context of current graph, which of the following options are correct? So Dijkstra's algorithm will return the correct shortest distance from S to all other vertices. Yes. So this is true. No problem. Hello.
Yes.
Correct
Sir,
problem.
so,
Yeah, tell me.
sir, so I have a doubt, sir.
Hmm.
So, Dijkstra's algorithm works even in case of negative weights unless there is a negative cycle, sir?
No. It is only general statement or specific statement. For example, general statement, if they're given without any graph, you're supposed to say that Dijkstra's algorithm doesn't work for negative weights. A general statement, like they are not specified any graph, just they have given a statement. I find out that true and false statement. Forget about this particular graph. Then what do you say? Dijkstra's algorithm doesn't work for negative weights. But this graph, consideration of this graph, this particular Dijkstra's will work. Is it right? Hello.
Yes, sir.
So the
Yes,
working
sir.
of Dijkstra's algorithm depends on the existence of negative cycle in that particular graph.
Exactly. But because author doesn't know when he is developed, because first algorithm is Dijkstra's, no, he doesn't
Yeah.
know. My algorithm works that for some kind of graphs. He doesn't know.
Right.
So that's the thing. He have given a general statement. So if they have given any kind of general statement like this one, you're supposed to say it is a false.
Okay.
Clear? But right
Okay.
now they already given a graph. In
Hmm.
this graph, context of this graph, the source is yes, it works because it is not creating negative cycle. No
Right.
cycle is existed. Frankly, it is no cycle is existed. Only it is, straightforward. S to A is there, but A to S is not there. We are safe. Now the next statement. Dijkstra's algorithm will return incorrect shortest path, that is from source S to at least one vertex because it contains the negative weights. So it is not incorrect because this graph is not having any negative edge weights, no? Clear? Sorry, negative cycle, no?
Yeah.
Is it? So that this statement we cannot select because they selected you that select the correct answer. And at extended algorithm for Dijkstra's is the Bellman-Ford. Bellman-Ford is exclusively another modern author. He said the Bellman-Ford is meant for the graph with positive weights, graph with negative weights also, because it can detect the negative cycle. So Bellman-Ford will return the correct shortest distance from S to all other vertices. Yes. And fourth one, Bellman-Ford will return incorrect shortest distance. No. Bellman-Ford is meant for, it is also single source shortest path. It is meant for detecting the negative cycles. The right answer is A and B are correct. A and C are correct. B and D are incorrect in this context of this graph. Clear? Okay.
So can you once explain again why only this graph, Dijkstra's algorithm will work for
See,
negative?
is there any cycle whenever negative weights are there? Is there any cycle? See, if you start it from yes, it's going to, for example, this is a source, this is infinite, this is infinite. Am I right? Hello?
Yes, sir.
This part you consider, because negative weights only we consider, but regarding that other things we don't consider. Now this 0 to -4, infinite is there, -4 is there, -4 is updated. Is it right?
Yes, sir.
So whenever it comes to that -4 to this particular A, so -4 and this one, it's going to be -1. Is it right?
Yes.
Yes,
So
sir.
this 0 to -2, so -2 and -1, which one is smaller? -2, no? So -2 is updated. Is it right?
Okay. Yes, sir.
Again you run it. Again you run it. Again you run it, or the same values will get it. Is it right? Hello?
Yeah.
Yes,
so-
sir.
Because values are stabilized. Hello?
Suppose I want the distance from S to F. What will it find?
S to F. What? No, no.
Yeah.
A to S. A to S is the better choice.
No, it's starting from S.
Ah,
Suppose I want to go to F.
where is F? Yes, I'll go to that. Okay. Yes. S to F. Is it
Yeah.
negative cycle is there? Let me check it.
Nothing to do with the negative. What will be the result?
Result.
Start at S.
Hmm.
Look for D will be the smallest.
Initially, it is a
-6. Infinite becomes -6.
infinite. Let me do that. Infinite. So it's going to be the 0 now. 0 to -6, so that infinite will go, -6 will come.
I come from D.
Wait. So then it's okay. That is okay. But there is another way. Maybe if you are going -6 and 7, it's going to 1. Is it right?
Correct. Yeah. It's
Now
1.
we go another way. So another way is that 0 to -4. It's going to be -4 now. From -4 to 3, it's going to be -1. Right?
That's correct.
So that -1 is updated. So that this is the smallest value comparatively 1. Yeah.
No, but
Again you run it. Are you the values are stabilized or anything changing? Again, if you run it, also same.
I'm talking about Dijkstra's.
Dijkstra's only.
Dijkstra, you don't keep running it.
No, actually keep don't running. But even you run it one more trial run, or same values you are getting, no? So to identify the negative cycle, you need to run one more. See, the Bellman-Ford is running n times. What you can call it is edge relaxation or something.
I'm not talking about, but I'm not talking about option 3rd.
Yes.
I'm talking about option 1.
Clear. But this works, no? This works, no?
No, option 1 it doesn't, right? It reached F.
Yes.
Once it reaches F, it stops, right?
Yes.
So from S to D, D to F, it reached with the reporting saying that it is 1. But it is actually wrong.
No, it's not 1. See, we are updating that S to D. D to S is updated. After reaching B, again, we have one more extent you are checking, no? See, there are 2 paths are there. Which one is optimized? That is updated. Is it right? See, for example, you started from S and we sorted out. After that, we started from B or not. Please kindly look at that. First, we are calculating from S to that, and then we are trying from B to that. B to that is calculated means already 1 is available. Whenever from B you are calculating, already existing 1 is there, -1 is there, whichever smaller. So -1 is updated.
We are taking that algorithm going through all the nodes irrespective of whether reach the destination. Is it?
Exactly. See, first time S to all, next time from the B to all, next time from the C. So then only optimized value are getting, no? Okay. Every time we don't run it from S. But S is having 3 adjacents. 6 is there. Sorry, B is there. A is there. Is it right? Is it there?
Yeah, that's okay. That's okay. Going through all the nodes again.
Exactly. So every node again, we are from that node adjacency we are checking. No, is it right? From the B adjacency you are checking. What is adjacent F? F is already updated with 1, but new value is -1. So -1 you are updating because minimum value. No? Clear? Now in this context, does the Dijkstra's works or not? It works. Is it right?
Yeah, it's working.
because there is no negative cycle. No negative cycle. If negative cycle is existed, Dijkstra doesn't work. Bellman works and reports, because after n number of cycles, still the values are not stabilized. It will report, sorry, there is a negative cycle is there, so please take care of it. It is not a stabilized value. And one more thing I'm telling you, if negative cycle is there, no particular algorithm can solve your problem, because negative will keep on going for negative. Only it will report. Is it right?
Right, sir.
Yes, sir.
Fine. So this is in this graph you need to consider. So don't consider general statement or specific statement, just you need to compare. But generally we don't give this kind of complex question. Only for understanding better, we are giving mock questions are somewhat complex questions, but the pattern of questions are very easy whenever you compare that this mock question and the actual quiz. So now let me go back. What is the next question? Yes. Oh, great. So here it is a general statement. See that question number 2?
Yeah.
Is it a general statement? Yes.
Yeah, it's a
Which
general
of the
statement.
following statements are true about Dijkstra's algorithm to find the shortest path? Is this author is given? The author main intention is to find out the single shortest path between the positive weights. So algorithm doesn't work for the graph with negative weight. So it is a true, because it's a general statement. Is it clear?
Yes, sir.
Yes, sir.
Now, it returns the shortest path between all pairs? Definitely no. So please understand, all pairs and in each pair is, so for example, A to B, A to C, A to D, something like this. This is called, so single source, always shortest is that, like that. Whenever that, all pair is there, for example, we have a graph like this, A and a B and a C and a D, something like this. So this is all pair means what happens, it tries to find out that A to B, C and D. Similar way, B to A, C and D. And similar way, the C, we are trying to find out that A, B and D. And the D, we are trying to find out the shortest path from D to A and B and C. So this is called all pair, but all pair is exclusively, there is algorithm called Floyd-Warshall. So this statement is definitely false. Is it clear? Now.
Yes,
Yes,
sir.
sir.
Hello. Yeah. So the shortest path returned by the Dijkstra's algorithm always passes through the least number of vertices. No, least number of vertices is not there. It tries to cover the complete path to find the reachability. You are reachable, but what is the optimized path to reach it? So there is no that least number of vertices. We try to find out that the edge weights is the main choice, because once that week number 5 you entered, all the graphs are introduced with weights. That's a week 5 concept we learned. Next one.
Yes, sir.
Next one. To decide that which node to widget, Dijkstra's algorithm selects that next smallest distance. Yes. Because from A to, what is the next smallest? From the B to, what is the next smallest? So in that way it will go, smallest distance. So this is also true. And the last one is, it can find that shortest path only for acyclic graphs. Acyclic graph, cyclic graph. So even you might have cyclic graph, no? Just now we have seen this graph. It's a cyclic graph, or it might be, there might be cycle is existed. Even directed graph, undirected graph, cycle must be there. Maybe cycle might be there. There is no rule that it should be that acyclic graph. So that it's going to be false. So the right answer for this one is A and D. This is because it's a general statement, not the specific graph they have given. Then you try to investigate. So that's a different kind of question. Yes. Now here that the Floyd-Warshall came. See, again, when I'm discussing about the Floyd-Warshall, it's a all source shortest path or multi-path shortest path, all source. Source is every time change. First A to all the vertices, then B to all the vertices, then C to all the vertices. Every time source is going to be changed. Now the question is, so true about that. So Floyd-Warshall algorithm. See, before going for Floyd-Warshall, so what this Floyd-Warshall is, running Dijkstra's algorithm for every vertex. So what exactly, the Dijkstra's algorithm is single source, only one source. Here, same Dijkstra's algorithm, if you run it for n vertices by changing every time source. First time A is the source, next time B is the source, next time C is the source. That is going to be the Floyd-Warshall. Is it right? Is it right?
Yes, sir.
So every time the source we are resetting. So every time we are resetting the source. That is called Floyd-Warshall. Please understand. So it can detect that negative cycles. Yes, because it is modern version of Dijkstra's algorithm. So it can detect that negative cycles. So after that n number of cycles, values are not stabilized, it means it will report. But here, the complexity you should understand. So what is the complexity of Floyd-Warshall? As I said, running of the Dijkstra's algorithm n times is going to be the Floyd-Warshall. Then what is the complexity?
N square.
N cubed.
No. N square is not right. N square means V square only, because V means number of vertices. So it's going to be the V cube or N cube.
N
Is it right?
cubed.
Because n vertices, you are running that n times Dijkstra's algorithm. Dijkstra's algorithm is already V square. So one more time this particular vertices you are checking. So V into V square times you are trying. So definitely it's going to be the V cube. So this is going to be the false. You can check it. Even you can open the algorithm structure or code structure. There are 3 loops are there, nested loops. Outer loop is there. Again, inner loop is there. There is innermost loop is there. That is what that Floyd-Warshall. So that B is going to be the false. This is false. So the first one is true. Now, it works correctly to compute the shortest path from I to J. It works correctly if the graph has a negative edge weights but does not have negative. See, as I said, no algorithm works that for negative cycles. Only it will report. Either Floyd-Warshall or Bellman-Ford, it will detect and it will report. But thing is, it doesn't work with completely accurate values for negative cycles, because if you run one more time, definitely the values are again updated again. So that's a ring. It works for negative edge weights, but it doesn't work with negative edge cycles. So it's going to be a true. This is going to be true. Sorry, that's a black color. It's a true. And the last one. See, one more interesting thing here in the last option. Now, whenever the Bellman-Ford, Floyd-Warshall we are doing multi-source shortest path, there is a dynamic programming approach is applied. Hope you recollect. The dynamic programming approach, what it will do is, it will take the previous shortest path matrix and compute the current matrix. Is it right? Is it right?
Yes, sir.
So here,
Yes, sir.
so every time the shortest path is updated. For example, let me tell you, this is A, this is B, this is C. For example, this is the particular graph is available. For example, this is I, this is J, this is K. So here, to reach from I to J, either you can go in this way, or you can go via k. Is it right? Is it right?
Yes, sir.
So here, what it will do is SP of k minus 1. What does it mean? You know, the previous calculated already available value. That is what k minus 1, k minus 1. K minus 1 means previous dynamic array which is already available. So here, please look at what I'll do generally. Out of this I to j, I to k and k to j, whichever the minimum one we are selecting. What I'll do, minimum of I to j is minimum, or so we have a reaching path. That is, reaching path is I to k plus k to j. These two is one sum. Is it right? Is it right? Because
Yes,
this
sir.
this is one weight is available. This another weight is available. This is weight 3 is available. Either weight 3 is smaller, or adding of weight 1 and weight 2 is smaller. Out of this, which one is the minimum we are selecting? Is it right? Is it right?
Yes, sir.
Now you check the formula. What they did, the previous matrix only they are taking, because to compute that current path, the previous values which is already there we are computing. But what they did is I to j direct one, I to k via k is right, via k is right, but here the plus should be here, here the comma should be there. Is it right or wrong?
Yes, that's right.
Yes. So here direct path of this is the direct path of it. This is via k, whichever is the shortest. So via k means I to k plus k to j, so that k is working like a mediator. To reach that j, we are reaching through that k, whether that path is shortest or direct path is shortest. So we try to compute means min operation, comma operator is here, plus operator is here. So there is some kind of what you can say that the particular equation they have done something changing of operators. That's only they did it. So definitely it's going to be a false one. So the right choice is that A and C. The right choice is, yeah, somebody wants to ask something.
Sir, could you please explain third option again?
So it works with the graph with negative weights. As I said, no particular algorithm is there. Whenever a graph with negative cycles is there, no algorithm works. Is it clear? Is it clear?
Yes, sir.
Negative
Yes, sir.
cycle is there means no particular algorithm works. But Dijkstra's algorithm doesn't report that there is a negative cycle is there. It doesn't report. Just it works. But whenever you come to that Bellman-Ford and Floyd-Warshall, it will report the negative cycle, but that is not accurate value. Is it right? Reporting will do. Sorry, there is a negative cycle is there. This values as not stabilized values. It is reported. Is it clear? Is it
Yes,
clear?
sir.
So that it is reporting you. Sorry, there is a negative cycle is there. This final result is not stabilized. That intimation it will. So that's the thing. It works correctly with negative weights, but it doesn't work. No algorithm is there till now. It works with negative cycles. Because values never stabilize. Whenever you run that one more time, definitely values are updated and new changes. So let me check it. Any question is there? Yes. So one more question is there. Maybe this is somewhat another interesting question, because still we are in the week 5 only. We are playing between Dijkstra's, Bellman-Ford, Floyd-Warshall. These three concepts only we are playing. We are not entered into spanning trees, because as I said, what are the important concepts are there. So consider this graph. So yeah, shall I proceed this one?
Yes.
Yeah, please.
Okay, great.
Yes, sir.
Yes,
Great.
sir.
Yeah, thank you. So now look at this graph. We are considered. So we are running this particular Dijkstra's algorithm taking source that is A. So now let me make it. Yes. So we are taking that A is a source. This is going to be the source. So what we do is, this is going to be the source. Yeah, this is going. Yeah, I'll delete everything because the last one I don't want it. This is going to be the source. Yes. So whenever you are computing the shortest distances, let me do that. The shortest distances is, so we are taking this as infinite, and maybe this is also infinite. I don't know what it is this. So we are updating this, means it's going to be that A to B, we are going with 1. So here this is the optimized one, which is going to be 2. Luckily we have all our positive numbers. So here it's going to be 3. From the D we have H. Please, everyone has to be mute. Yeah. So here this reaching of this particular D is 6 here, because already 2 is there. 2 plus 4 is 6. So if it is reaching through this E and some mute is important. Yeah. Cool. So here, so whenever you reach that H, there is a way that A to D and then 4, then after reaching this E's reachability is that 4. After reaching 4, this is going to be 5 is optimized value. Is it right? Is it right or wrong?
Yes, sir.
Yes,
Because
sir.
Yes, sir.
A to D, D to H is 6. But
Right.
whenever you are reaching D and then after that E,
From
then
A,
after this one is, hello.
from A, it should go to B, right? B is the shortest.
Oh, sorry, still it is shortest is there.
Yeah.
No.
It is
I'm calculating for the H, reachability for the H I'm calculating. What is the
Right.
best value?
Yeah, it should go to A, B.
But it is not optimized. Is it optimized? It's a 4 value, no, you are getting.
Okay.
We are trying to find out for the H, no, because infinitive we want to clear it. Clear? So now let us go for the H, sorry, F. So whenever that F we are calculating, it's a 7 is optimized, I'm thinking. Let me check about that. Any other better value? I think 7 is still now. Now for the E, there is 3 and this is 10. Okay, 4 is already updated, no? Yes, it's already 4 is updated. So now 4 is there. For the B is already updated, but last one I think it's a G or something. The G reaching is, it's a 7 and 9. It's a 6 and this. So that 7 is optimized, I think. I don't think, yeah, 6 is optimized because 2, 4 and 6. So this is 6 is optimized. Up to this, is it clear? Is it clear? Let's see the questions.
Yes, sir.
Yes, sir.
So now, what are the questions are there? Because, yeah. Okay, maybe that's not issue. If A is the first visited vertex, what is the 7th visited vertex? So then the 7th visited vertex is G or not? Let me find out. Is it G or not? Is it G? Let me check it. So what is there? If A is the first visited vertex, so 7th visited one is that A. Sorry, I'm sorry. Yeah, it is. They asked about the first. Maybe the sequence numbers. I'm taking a different color. Yes, it could be different. This is the first vertex. After the first vertex, the nearest one is 2, second vertex. Is it right? This is the third vertex. Is it right? I'm giving sequence numbers. Hello.
Sir, wouldn't D be the third one?
Yeah.
Third will be D.
Oh, sorry. I'm
Yes,
sorry.
sir.
Yes, I'm sorry. You're right. So third one will be D. Correct. Okay, this could be third one. Sometimes Epic will create a trouble. Yeah, third one is D. Fourth one is C. it's okay. Now it's playing. It will make me trouble sometimes. Yeah, it's okay. Wait, I'll clear this one. Maybe it is creating a problem. So I'll stop this epic actually. Maybe it is hanging my machine. Yeah. Okay. So this is the first one. So when it comes to that B is the nearest one, second vertex. Third one is because it's a two smaller value, third vertex. And this going to be the fourth one. Okay. So then after it, fourth one. Then here it is 10 value. Here it is after reaching this D. From the D, E is going to be the distance of 4. So reaching this 4 and this is 10 and this is 4. So that this is the fifth one. Am I right? Is it fifth one or not?
Yeah.
Hello?
Yes, sir.
Yes, sir.
This is sixth one, if I'm not wrong, because the value is 4 plus 4, 2 plus 2 and 4, and this is 5, so that it is optimized value. After 4, H is going to be the sixth one. And seventh one, so reaching up this particular F is 3 plus this, what it is, 7, so that it's going to be the sixth one. The reaching of this G is here, 1 and 2, 7.
7.
Wait. Out of these two,
6,
which one
sir.
is? Wait. Let me check about it. So the reaching of this particular one is F is 7. But the reaching of this one is 6. So what is this seventh node is it G or not? Hello.
Yes, sir. Right.
Yes, sir. It's
The last one is eighth one is this,
Eighth,
because it is the longest distance comparatively using the wedge weights. Now the particular question is clear. Yeah. So if A is the first visited one, then seventh visited one is G. Is it right?
Yes, sir.
Sir,
Yes, sir.
It's a true. So we can put that. It's a true. Next one.
sir, how is F8 like?
Because
The
it's a
distance is
last distance is that one, no F, no? Highest distance is there comparative to all.
How like A to C and then C to F?
What is the distance? Value 7, no?
Yeah,
7. So what is the value for the Z? 6. Is it right? Don't calculate the number of edges. It's not BFS or DFS.
yeah, it's 6. Yeah.
It's edge weights, no? Clear?
Yeah.
The shortest path from that cost from that A to H is 6. Is it 6? No, it's a
False,
5.
sir.
It's a 5, no?
Right, sir.
It's a 5 or 6? 5 is the optimized value.
5.
So that second one is false. So A to G is 6. It's a true. Is it right?
Yes, sir.
Yes, sir.
More than one path exists from A to H with same minimum cost. A to H is the same minimum cost. More than one is there. 6 is there. We have another way. 7 is there. Same weight A to H is there. 6. No. 5 is there. 4 is there. No. I think it's not there. A to H, is there any similar edge weight is there? Same minimum cost? Only we have that A to H minimum as it is 5. Is it right? Any better values there?
No, sir. Right, sir.
Hello. A to H is that minimum one is 5. Any better values there?
No, sir.
Is it 5? No.
Yes,
Yeah,
sir.
it should be 5.
It should be 5, and any better value is there? No, definitely. But similar 5, another way is there? No. See, another 5 is there? No, no chance. Even to reach that, So 1 to D, and D is 4, 4 and 4, 8. No chance. It is 6. So A to D, D to E is 4, E to H is 5. So that this option is wrong. There is only one path from A to G with minimum cost. A to G with minimum cost. The minimum cost we already found is that A to G is 7. 6. Is there other 6 is there? No, I don't think other 6 is there. Only one. So that this is also true. Is it clear? Only one,
Yes,
no?
sir. Yeah.
Yes, sir.
So here more than one path they asked it. Here only one path they asked it. So here only one path is existed, but they asked about more than one path is available. Definitely no. Here one path is available. Yes, it's true. So actually I did not submit it. Maybe later sometime you submit, but I'm not submitting right now. Yeah. So here same question, which is what is the wrong with it? The same question, which is which of the following true about that Floyd-Warshall? So it can detect that negative weight cycle. Yes, any negative weight cycle is there, definitely it can detect it. The time complexity is not V square, it's a V cube, because n times you are running the V square, because every vertex we are trying to pick it out as a source and try to find out the shortest path. It works correctly with negative weights, but does not work with negative cycles. Yes. So this formula is wrong, because as I said, the operator comma and plus operator is used in the wrong place. That's what it is wrong. Yeah, I think it's okay. Yeah, still maybe some questions are there at my side. Then we'll come back to here. Yeah, this is interesting question. Adjacency matrix we are creating for a graph. So quickly you create it, because maybe it's a complexity question, but why do you meant for this question is, while you are solving the question, you will recollect all of your concepts. See, it's a adjacency matrix. If it is adjacency matrix, let you consider the vertices are these. Maybe it looks like this. Is it right or wrong? Is it right? Is it right?
Yes, sir.
Yes.
Yes, sir.
Now, maybe you are trying to draw a particular graph like this, 1, maybe 2, 3, and 4. So as per that, maybe they have defined 0 to 1 is 1, because there is 0 to 1, they have given his weight is 1. Similar way, 0 to 2 is there, that's 8. So 0 to 3, they have given it, maybe it is 1. And then, so 0 to 4 is given, that's a 4. This is 1. So then after it, we are trying to connect with 1, because once this is over, then we try to connect with 1. So 1 is connecting with 0, it's already there. 1 is connecting with 2 with a weight of 12, maybe like this. Then 1 is connecting with 3 with a weight of 10. 1 is connecting with 4 with a weight of 9. Yeah, it's right, 9. So that's it from the 1. Next we are going with 2. So 2 anywhere, 0 we are connected, 2 with 1 is connected, 2 2 is not there. 2 to 3 is there, 2 to 3 is 7. So we are connecting these two, which is 7. So then after it, 2 to 4 is available, that's a 3. That's a 3. So then after it, we have the last choice of that 4. 4 to 3 is pending. 4 to 3, it is connected with 2. Up to this, is it clear? Is it clear?
Yes, sir.
Now, they are trying to find out the minimum cost spanning tree. What is the minimum cost spanning tree cost? It's a very simple. Let's apply the Kruskal algorithm. So the Kruskal algorithm is simple. All of the edge weights are there, whatever edges are there, that edges are sorted based on the weights. So sorted based on the weights, and we are trying to pick out that particular edges, and we are adding it to minimum cost spanning tree if it does not form a cycle. If it does not form a cycle, Is it right? Is it right? Hello.
Yeah.
Yes, sir.
Kruskal algorithm is sorted edges are picked up, like ascending order. So whenever the particular edge weight is not forming a cycle, we are adding into spanning tree. Now, first minimum edge is what? It's a 0 to 1. Is it right? Because its a weight is 1, no? Is it clear or no? Hello. It's a sorted order. Hello.
Sir, could you please repeat again?
What is the Kruskal algorithm is the edges are selected in ascending order because sorted weights are selected. If the particular edge doesn't form a cycle, we are adding into spanning tree. Is it clear?
Yes, sir.
Out of all these are sorted, what is the smallest value?
1.
Okay, so what first edge is 0 to 1, so that we are selected this. Another one is there, no? Is it right? Another one edge
Yes,
is there. What is that? 0 to
3.
is it
3.
forming? Is it forming cycle? No. So
No.
we are selecting 0 to 3 also. So another edge weight 1 is selected. What is the next smallest one?
2.
No, 2 means the edge source and destination. Please tell me.
3 to 4.
Exactly. So we are selecting 3 to 4. This is the edge. 3 to 4 edge. The edge weight is going to be 2. Is it forming cycle? No, no problem. Next one. What is the next one?
2 to 4 we can go.
2 to 4. So 2 to 4, which is there. Here it is 2 to 4. What is the edge weight?
3 it is.
3.
It's a 3. I think all of the particular vertices are connected. So is it a spanning tree? Yes. So
Yeah.
what is the cost of this? It is going to be 5 and 7. So the result is that 7. The answer is 7. So if it is forming cycle, we don't select it. For example, another one is here, for example. Will you select it or not? We don't select it, no?
No,
Is
sir.
it
No,
right?
sir.
That's the thing. So we are selecting the edges in the ascending order. We are putting into the each edge into the particular MST. If it doesn't form a cycle, we are considering as MST. Otherwise, we don't consider. So that's a particular question number 4. Now, yes. Yeah, please.
So I was saying that basically, according to the last example you used, if there was a edge from 1 to 3 with the weight 1.
Wait. Somebody who has just raised the hand because everybody. Yeah. Hello. Yeah. Tell me.
I was asking, according to the last example that you used, if there was an edge going from 1 to 3 with weight 1, we wouldn't have used that because it wouldn't result in a MCST.
Correct.
Okay.
Because
Okay.
it is forming a cycle.
Yeah. All right.
Yeah, fine. So now maybe another question is there using MCST. Please look at here. Here, this question is somewhat interesting. What exactly, this question is, they have already given, wait, the edge weights, no? Wait, correct. Let's G, the graph, which is complete undirected graph with 4 vertices and 6 edges are there. Like, 6 edges. And edge weights are given 3, 4, 5, 6, 7, 8. 6 weight edges are there. The maximum possible total weight of minimum cost spanning tree. Maximum possible minimum cost spanning tree. See, spanning trees are multiple. One graph might have multiple spanning trees. Am I right or wrong?
Right, sir.
So out of that, what is the maximum possible minimum spanning tree we need to find out. So look at, I'm quickly drawing this 3, 4, 5, 6, 7, 8. Yeah, it is 6 edges. Yeah, it is continuous sequence of values. No problem. 4 vertices. So as per the question I'm going, let me open another wrapper because I don't want to disturb everything. Yes. So they are said it is 3, 4, 5, 6, 7. Maybe, graph, it looks like this. There is 4 vertices, 6 edges are there. Let me have that. Something like this 0, 1, 2, 3. So maybe 4 vertices are there and 6 edges are there. We don't know which one belongs to what. The weights are given. The weights are given is something like this. So 3, 4, 5, maybe 6, 7, 8. Is it okay? Is it okay? Because they did not tell
Yes,
you
sir.
that which particular weight belongs to which particular edges. Directly
Yeah,
3,
yeah.
4, 5, 6, 7, 8 is given. Now the
Yes,
question is, minimum cost spanning trees are possible, multiple spanning trees are possible. So what is the maximum value of minimum cost spanning tree? Now, let me consider maybe edge 3 we are considering, because always we are selecting minimum cost spanning trees in ascending order of Kruskal algorithm, because the shortest algorithm is like, and easiest one is that Kruskal, selecting the edges in sorting order, like ascending order. So what is the first edge we are selecting is, we are selecting 0 to 1. Is it right? Is it right?
Yes.
So definitely we are selecting the first edge, definitely it doesn't create any cycle. Is it clear?
Yes, sir.
Yeah.
Now the second edge also we are selecting, no problem, because second edge between 3 vertices, 2 edges doesn't create cycle, no issue. So this is also can be selected. Fine.
Yes.
Now third edge, maybe 1 to 2 might be there, or 2 to 3 might be there. Is it right?
Right, sir.
So if 1 to 2 is there, what exactly, if this is forming cycle, the edge 5 we are not selecting. Is it right?
Yeah.
Yeah.
If
Cycle.
edge 5 is not selected, there is one option is there. We have to select that edge 6. Is it right or wrong?
Yes.
So
Yes.
we supposed to select this edge 6. This is the first case. Sorry, it's a 3. It's a wedges 6. This is the first case. So in this case, the MST is formed. Is it right?
Right.
So what is the value we got? It is 13. MST value.
Yeah.
Fine. Now, if edge 5 is not forming cycle, maybe 0, 1, maybe you are having 3 and we are having 4. So here that value 5 might be there. Here might be 4 is there. Here might be, sorry, 0, 1, 2, 3. Yes. So here might be 6 is there. Here might be 7 is there. In this case, what happens, 0 to 1 is selected. No problem. It's a 3. 0 to 2 is selected because second edge also doesn't create between 3 vertices. So this is also not forming cycle because this 5 also selecting, no problem. In this case, MST value is 13. In this case, MST value is what? How much? 12, no?
12.
So what they ask that the maximum possible value of the minimum cost spanning tree. Hope you understand. Hello? Hello?
Yes.
The maximum possible value of the minimum cost spanning tree is this. We don't get spanning tree more than this value. So if they ask directly minimum cost spanning tree, 12 is the right answer. Hope you understand. Clear? Hello?
Sir, but since we don't know that the
Yeah, we don't know the
which
graph.
edge,
We don't know the graph. That's the reason we try to draw the graph and maximum possible value is 30. We don't get more than 13 value. You check it. Because to connect the 4 vertices, 3 edges are more enough. Am I right or wrong?
but those 3 edges can also be 6, 7, 7, 6, 8,
No,
right?
no, not possible because already given the values are 3, 4, 5, 6, 7, 8 sequence order. No?
Yeah.
If I change the
Uh,
sequence order.
No. It's a sorted. Always Kruskal algorithm, it is sorted. Even you try with the prims also same.
Okay, all right.
Clear? Because
Yeah.
always we are going with the minimum value because how can you get that minimum cost spanning tree? Always we are greedy to select that minimum cost only. We are greedy about the selecting the minimum value. Clear?
Right.
Because it's a greedy approach. Yeah. Sorted and then selected because just like our greedy method. Yeah. So this is definitely the value of 13. Yeah. So this is 1 mark question. Maybe let me go back our maybe previous question. Anything is there? Some important question. Maybe we miss it. Yes, this is one more interesting question. So maybe, yeah. Okay, I'll erase this. Yes. Okay, that's not a problem. See, look at here. My general question is, don't think about this particular question. Prim's and Kruskal is there. Whenever a graph is given input for the Prim's and Kruskal, we want to generate the minimum cost spanning tree. Does the both algorithm result the same or any different kind of graphs? Same graph is given input. Does the result of that MST is same or different?
I think it should give same.
Yes, it's the
Same,
same.
sir.
It's the same. It's the same. Whenever the same particular graphs are given, like their weights and their shape and their connecting edges, all these are same, means you will get it that same kind of graph and same kind of MST value. That's what, please remember. Now, so suppose we run the Prim's algorithm and Kruskal algorithm on a graph G and with the distinct weights. Luckily they said it's a distinct weights. Distinct weight means 1, 2, 3, 4, 5, 6. There is no duplicate values. And these two algorithms produce minimum cost spanning tree. The spanning tree names are the tree Prims, the tree Kruskal. That's what TP, TK. The tree generated using Prim's algorithm, the tree generated using Kruskal algorithm. And the value of the minimum cost also calculated, the calculated or computed value of Prim's, the calculated or computed value of Kruskal. Yes, we got it. Now, which of the following statement is true? So one statement is true. That is, the tree Prim's, tree Kruskal are the same. Yes. But the CP and CK are different. No. You get the same trees, same computed values also. Now, TP may be different to TK. No, definitely no. This is also false. Both are same. TP and TK always same. Yes. And the computed value of Prims and computed value of CK also same. So this is the right answer. And the last one is TP and TK are different. CP and CK also different. No. Because same kind of graph, if you taken as input for both algorithms will generate same spanning tree. Both algorithms will get the same spanning minimum cost spanning tree result also, computed value also. That is what the Prims and Kruskal. Only the approach is different, but the complexity and the computed one is same, because same graph if you taken as input, same output you will get it. So that is what exactly the Prims and Kruskal. So now let's go for any quiz question, sorry, mock quiz question is there. Maybe, it might be suitable. Maybe it will solve it in the mock. So question number 6. Yeah. There are 20 nodes. Yeah, it is. Somebody will. Yeah. Look at here. There are 20 nodes where the number of nodes in the child nodes is 7. No, let me finish up this. Maybe it belongs to some other concept. Yeah, we'll finish up this, then we'll get back. Right.
Excuse me, sir.
Yes.
You said like the Prims and the Kruskals will both give exactly same output and the result. So when should we apply Prims and when should we apply Kruskal?
There is no rule, like, Kruskal algorithm is sorted and doing it. But Prim's algorithm, each particular vertex is selected as a component. From the component, we are selecting the next minimum edge. That's it. So both of them are same. like each particular vertex is considered as a component, and then we do component test. See, you can check it, both of them. One is not alternate to other. They are different approaches. That's one is not better than other. Only thing is two different approaches. Okay.
Okay.
Yeah.
Sir, I have a doubt.
Mm-hmm.
If the edge weights are not distinct, then also will this hold true?
But
or?
here, then what happens? Whenever edge weights are different, similar. What exactly? Duplicate weights are there. There are chance of that multiple spanning trees with same cost you will get it. Is it right?
Yeah.
Then we cannot guarantee. Prims will generate a different spanning tree, and Kruskal will generate a different spanning tree. But spanning tree value is same.
Okay.
Clear?
Okay.
Yeah.
Okay.
Just maybe I'm not able to erase this. No. Eraser.
Sir, can you show that graph for previous question?
Wait, I'll show it. And this part is not there. Where is it? We close this. Somewhat it is creating a problem, so I will quit this. Yeah. I'll open this one more time because it's creating a trouble to me. Just I'll delete this. Again, I'll draw it, not issue. Page. The screen is not clear actually. On the screen, it should not be there.
So, sir, close that note, that OneNote app completely and relaunch.
That's what I'll do. Yes, now it's okay. Yeah. So yeah, somebody has a doubt that yes.
So
Here
that
is that.
mock question.
Yeah, just a minute, I'll go back to those. Yeah, it's okay. Up to this is clear. Question number 5.
Yes,
Hello?
sir.
Okay, just a minute. I'll go.
Yes, sir. Crystal clear.
Yes. I'll go with the mock question because there is a rough work I'm taking. There is some rough work. Yes. Another rough work I'm taking. Yes. Yeah, mock question I'm going because somebody has something doubt about it. Yes. Yeah, this is the question, 3, 4, 5, 6, 7. Is it correct question? Is it right?
Yes, sir. I want to know how you conclude on the graph because you randomly draw it.
Yeah, it is okay. So it is definitely 4 vertices and 6 edges. Is it right?
Yes, sir.
So that we are sure we can draw that. We can draw that any particular graph, maybe 0, or it might be A, B, C, D. 6 edges means any possibility other than this, only this possibility, no? Is it right? Any possibility?
Yes, sir. This is
fine. So now it's clear. So you want to give that values of the edge weights. The values of the edge weights are clear. They are given directly. That is 3, 4, 5, 6, 7, 8. So that 6 edge weights. Can you put 2 here? Can you put 3 here? Can you put 4 here? Can you put 5 here? Can you put 6 here? 7 here?
Oh, okay. So because the graph is closed, we can
Sorry.
put the number.
What they've given? 3, 4. No, sorry. I'm sorry. Yeah. Yeah, it is okay. Yeah, it is. This is.
Oh,
Yeah, it is 3. Yeah, it is. They started from 3. 3. Okay. 4 here. 5 here. 6, 7, 8. Now my question is, to connect two vertices, how many edges are required?
1.
Fine. To connect that 5 particular vertices, how many edges are required? Minimum.
4.
4. Because n minus 1 only. Simple logic. Simple logic is
Yeah.
n minus 1. Now, to connect these 4 vertices, how many edges are required?
3.
3.
So 3 we are selecting. So the first one is, we are definitely selecting the minimum because we are choosing the Kruskal algorithm is the easiest way to create MST. So the minimum one we are selecting is between A to D. Is it right? Definitely one edge doesn't create any cycle. Is it sure?
Yes, sir. Yeah.
Second edge also doesn't create cycle because between the 3 particular vertices, 2 edges doesn't create cycle. No problem. So that second edge I am selecting the sorted order. That's going to be that between, I'm sorry, actually I've chosen this wrong. This is 4 and this is another one. Is it right?
Yes, sir.
So this is 3 and 4. Yeah, it is okay.
But there is no connection.
Wait. C and B. Is it right? Is it right?
Yeah. Yes.
This is 3. This is 4. That's okay. Now, still one more component is required. So one more component we are selecting is this one, like C to D. C to D, if it is connected, is it forming cycle? No. Is it right?
Yes, sir. It's not forming.
So that it's not forming cycle means we are selecting. So minimum cost spanning tree we got it as it's a 12 total. Is it right? 3, 4,
Yes,
5.
sir.
But there is a chance. There is a chance means maybe another graph is there. We select another graph as maybe A, B, C, D. So where you have here there might be a cycle like this is 3, this is 4, this is 5. So rest of things are same, 6 and 7. Is it clear?
Yes, sir.
Now,
Yes, sir.
now selecting this particular 5, definitely it creates a cycle. Is it right or wrong? Is it right?
Right.
So other than 5, what is the choice? 6 is the choice. So then what happens? We are selecting 3, we are selecting this 4, and we are selecting this 6. So total is going to be 30. So they asked you that maximum possible spanning tree value for minimum cost spanning tree. What is the maximum possible value? Is 30. Is it right?
But sir, total maximum would be the largest edges, largest
No.
edges.
Sorted order only we are going sequence. No.
Okay. Oh,
So
in
even
the sequence of increasing order.
Even not only because we are selecting Kruskal, even you select the prims also. For example, components are like this. What is the prims is telling? It's a components are divided. First from this component you select at whichever minimum. Either this one is minimum or this one is minimum or this one is minimum you are selecting. Is it right?
Yes, sir.
At that time also we get minimum only, no? Is it right?
Yeah.
So any vertex you select as independent component, the next component you are selecting is that which is the nearest minimum component, minimum component edge weight we are selecting. So at that time also we get minimum only. So out of these 3, 4, 5, we are selecting first 3 only. Because if you started from this particular vertex, that is called prims.
Okay.
Even prims also same. Only
Also,
the approach is.
It should not form cycle, right, sir?
Yeah, it is okay. No particular MST when you are selecting a edge, that edge should not create a cycle. Then only we add it into MST. Otherwise, we don't add it. We go for next edge. Clear?
Okay.
Yeah. Understood, sir.
Yeah. Cool.
The question is asking for the minimum from the maximum, right?
Yes, exactly. Minimum
Yes.
possible. Sorry, maximum possible spanning cost for a minimum spanning tree.
Okay.
Maximum possible weight. Okay. Yeah. So here, this before this going, so because some standard questions are there, let me finish up that. Then again, we'll come back to the mock, because coming to the mock is not a big deal. That we can get back to here. Some interesting questions are there, which are similar. Yeah, this is okay. This is one more question. See, look at here. Yeah, it's okay. See, look at here. Consider an algorithm. They did not tell you the algorithm. What is the algorithm is? So a connected weighted graph with n vertices and m edges. We don't know how many vertices are there, how many edges are there. So m number of edges and n number of vertices. Now, the thing is, what we want to do is sort the edges based on that edge weights in the decreasing order. So the decreasing order of the edge weights we are doing, decreasing order of the edge weights, if you do it, maybe, you know, not increasing order, decreasing order. Maybe edge weights, let you consider, this is 6, 5, 4, 3, 2, something like this, because it is descending order they sorted. Consider that Ej in the sorted order. We consider that edge j, whatever that edge j, this is going to be the Ej, edge j. They are edge weights. What this particular one is edge weights, because they are sorted in the reverse order. If the edge is not a part of cycle, then delete it. If the edge is not a part of the cycle, then delete it. Otherwise, keep it in the resulting graph. Now let us consider. So maybe, you know, we consider that same, you know, whatever 6 edges are there, we consider that A, B, C, D. We are taking one example, maybe same example or something. We are considering maybe, you know, this is 1, 2, 3, 4, 5, and 6. Now we are considering the first edge. First edge we are selecting is 6. Is it participating in the cycle? First edge when you are selecting, is it participating? See, the edge is, if the edge is part of cycle, then delete it. Is it participating in the cycle or not? 6, is it participating in the cycle or not? It's participating, no? Hello? Hello, am I in the call?
Yes, sir.
That this
Yes,
particular point I'm trying to solve it. If edge is a part of cycle, then delete it. Now the 6 is part of cycle or not? Because 6 is forming a cycle. Like this particular part is cycle. Is it right?
Yes, sir.
Similar with this part also cycle. Is it right?
Right.
So we are deleting this one. We are deleting means we are deleting the 6. Now, next we are repeating the same. We are keep repeating the same particular one. We are repeating. So we are repeating means the next stage we are selecting in the descending order is this 5. This 5 now you are selecting. Hello, 5.
Yes, sir.
So now 5, is it the part of the cycle? Because 6 is removed. Once 6 is removed, is it part of cycle? After
2,
removing
4,
6,
5, 2, 4,
5
5.
is, hello.
Yeah.
Uh,
A, C,
It
D.
can be, sir. It can
Yeah,
be.
it can be part of cycle, no?
Yes.
So
Yes, sir. Yes,
I
sir.
can remove that 5 also. Is it right? So that
Yeah.
this is also removed. Next one 4 I am coming. So after that 5 is removed, 4, is it participating in the cycle?
No,
Yeah,
sir.
No,
it is.
because already 5 is gone. 2 and 4 is there, no problem. It is not forming any cycle. So 4 we can leave it, so that we are giving permission to 4.
So
Next one.
in A,
Hello.
B, C.
Wait. Let me finish up that.
Okay.
Okay. Now we are coming to the 3. 3, is it participating in the cycle?
Obviously, sir. Yes.
Yes, because it is participating in 1, 2, 3 cycle. So that we are deleting this one also. So that this is also deleted. This is also deleted. This is also deleted. What is remaining? 1, 2, and 4. 1, 1, 2, sorry, 1 and 2 and 4. So it looks like the tree is A, B, spanning tree it looks like D. So this it looks like this. Is it right? Is it right? Hello?
Yes.
Yes, sir.
Here what they did is the reverse order of the Kruskal algorithm. Hope you know that. The Kruskal algorithm, what they did, every time you are selecting the edge which is in the ascending order, if it is not forming the cycle, we are including. If it is forming cycle, we are not including. So what they did is they are deleting from the descending order. If that is participating the cycle, you are deleting. Hope you understand. That is clear. This algorithm is clear.
Yes, sir.
Now the questions you see that MSQ. So exactly m minus n plus n plus 1 edges are deleted. So what is my n number of vertices? Already I have taken 4. M number of edges is 6. Example I have taken this, but it is proved. It is a proved. Let me check it. So m minus n. So m minus n means 6 minus 4 plus 1. So what is that? 3. Is it 3 edges are deleted or not?
Yes.
3 edges, no? This 6 and 5 and 3 are deleted. So this is a true. Even you try with other graph also, same result will come. Next one. At most, n minus 1 edges are deleted. So n minus 1 edges, is it true or not? N minus 1 edges. So my particular, vertices are 4. So how many edges are deleted is n minus 1 edges. Is it always true? Deleted
Sir,
edges is how many? 3.
sir, in the first option, M is 6, right?
M is 6, no? Edges are 6. I've taken
Okay.
6 edges. So n number of it. So that m minus n plus 1. So that it is going to be 3. So 3 edges are removed. That is clear. Now, at most n minus 1 edges. At most means what? Minimum or maximum? It's a maximum, no? Maximum.
At most maximum.
Maximum.
Maximum. So maximum it is n minus 1 edges. Is it possible like less than that n minus 1 is possible? At most?
No.
No, sir.
Can you do that? Like n minus 1 means currently 4 is there. Can we do that?
Maximum.
4 minus 1, 3. Can we
Maximum
delete 2? Can we delete 2 to create that spanning tree?
No.
No, sir, because
it's
there
not
will be a
possible.
cycle.
It is not possible. Still cycle is existed. So this is going to be, yeah, this is going to be the false.
If
Next
there
one.
would have been exactly, then exactly
No.
n minus 1 edges.
Exactly n minus 1 means right.
Yeah.
That's it.
Okay.
Now, after processing m edges, the resulting graph is connected. Yes. Minimum cost spanning tree is a connected graph. Is it right? It's not a complete graph, but connected graph. Am I right or wrong?
Yes, sir.
It's a connected graph, no? Hello.
Right, sir.
It's a connected graph. Clear. So what remains end of that particular one is minimum cost spanning tree. Yes. Because the remaining what is pending is it's a minimum cost spanning tree only. Is it right? Because it's a reverse order of that Kruskal algorithm, no? Last one. After processing all m edges, the resulting graph has exactly n minus 1 edges only. See, what you said is, this one I said it is false, no? This one I said false. Is it right? This option?
Yeah.
This one is a true. Exactly, we have that n minus 1 edges are available. Here deletion is different, available is different. So available is definitely to connect that n vertices, you require that n minus 1 edges only. Am I right or wrong? Hello.
Yes.
Clear? Yeah. But this is at
Yes,
most they said it. At most they said it. Below that it is not possible. So at most is not right, but exactly is right. So actually, sometimes even 3 particular vertices are there. For example, let me take that A, B, and C. This is the graph. To create the spanning tree, we are trying to delete that at least one edge. Am I right on? So one edge you are removing means it's not that below that what exactly n minus 1. It's definitely it is equal to n minus 1. Is it right?
Yes.
Wait. There is a confusion here. There is a confusion. Please wait. At most n minus 1 wedges will be deleted means maximum is n minus 1. So minimum could be less than that. Is it right?
Yes, sir.
So in this case it is true, no? Is it right?
Can I ask something?
Yeah, you can.
So the edges that will be deleted and the edges that is remaining, that will always be equal.
No, remaining is definitely n minus 1 is true. That's a truth. That's universal truth. Clear? Okay. Connected graph means n vertices requires n minus 1 edges. The deleted they are talking about. How many deleted here? 1, no? 1. Is it
yes.
right?
Yes.
Does this one is less than or equal to n minus 1? It's a true, no?
Yeah, it is less than, yeah.
Because it is at most they said it. Maybe I think at most is some kind of complicated grammatical sense.
And so okay, so the statement says if the statement will say exactly n minus 1 edges will be deleted. So this particular
that is false. That is false.
Even for the graph for this particular like A, B, C, D, that graph.
No, that graph is okay, but all graphs it has to
not
be
for
equal.
all graphs, right? Yeah.
It has to be.
Generally, it is not true. Yeah.
Yes, this is the one particular one example. So exactly n minus 1 you are deleting means you're supposed to delete that 2 edges. Is it right?
Yeah, got it.
So that I think there is a mistake in this particular word. I think so.
So at most can never be like true. At most can never be true.
It is actually that's wrong.
Yeah.
At most they should not use it. Grammatical issue. Yeah, it is okay. Now, maybe I think why my screen is not clear.
Close the app and reopen, sir. Yeah, OneNote has some like lot of books.
Dialog book is there? Oh, 2 times it's there. Oh, it's there only 1 time. Yeah, it's okay. Maybe that's not issue. Again, I'll open what is there. Is it clear up to here? Shall I go for the next one? Yes. So I
yes, sir.
Next. Some mistake is there. I don't know. It's not clearing. Yeah, let's let me fix this. So up to this is okay. Yeah, it is. Yeah. Now jump into this. So now let's directly don't go for the heaps because we have to finish up this particular MST part. If any question is pending in this mock, yeah. After that we jump to the binary trees and all. But this could be the last question of this trees and all. Up to this is okay. Yeah, it's okay. Maybe now.
How much have we covered, sir, in week 5 and week 6?
Week 5 everything is covered. Now week 6 we are entering.
Okay.
Week 6 is trees, no? Clear? Week 6 is trees and heaps. Is it clear?
Yeah.
Yes, sir.
Now we are going. Yeah, now we are going. This question is the question number 7, which is about that heaps. See, look at. Hope my screen is visible. Little bit zoom. Is it okay? Yeah.
Yeah, it's okay.
See, look at here. Max heap and min heap properties. Basically, it should be a complete binary tree. Complete binary tree means we are trying to fill all the particular nodes from left to right for all levels except the last level. Is it right? So complete binary tree means what? No. From the root to all levels except the last level, we try to fill it all the particular nodes. Like this is a complete binary tree, what you can call it. This is a complete binary tree, except the last nodes. Is it right? It's a complete binary tree, no?
Yes.
Yeah, fine. Now, the max heap property is it should be a complete binary tree, and as well as the root must be greater than or equal to its children. Maybe you can consider as a greater than. Always root must be greater than its children. Now, instead of 2 children, they consider as 3 children. 3 children means what it contains, the root, it contains 3 children. Again, this particular subordinate, it contains 3 children. This way it is there. Is it clear? Is it clear?
Yeah.
Now the situation is how to find out that left descendant of the current root is 2 into I plus 1. Is it right? Hello?
Can you comment that again?
So how to find out that left descendant of a root, left of root, right of root, is this way we are finding out whenever 2 children is available. Is it right? For example, this is 0th index, first index, second index. Is it right?
Yes.
Because in the heap it is a list of values is there, no? Is it right? How to find out the left of the root? 2 into I 0, that is 0 plus 1, 1. This is the left. 2 into I, this is 0, I is 0. So that is true, that is the right descendant. So whenever 3 descendants are there, this is 0, this is first, this is second, this is third. How to find out the third descendant is, so 2 into I plus 3. Is it right? First descendant, left one, centered one, right one. Is it right? Is it clear? Up to that's clear, no?
Yes.
Now, if the root is 0, what is its next level left to right? It looks like this. First one is left one, second one is centered one, third one is 3. Is it right? Is it clear? Because to understand that, they are telling you what is this 3 array concept, max heap with 3 array. The node from the second level from the root is going to be the 0, because this is from whenever this is the next level, that is, this is going to be the 4th one, 5th one, 6th one. Is it right?
Yes.
So similar way, the next one, it goes to 7, 8, 9. So that's what max heap or heaps are maintained using the Python list. Now, suppose we have that 6, 1, 12, 8, and 9 are inserted in the order of the 3 array of the max heap. Already max heap, this one is available. After the max heap is available, we are trying to insert 6, 1, 12, 8, and 9. So what is which of the following sequence is representing the resultant? Now let's create. First, basically, this heap we are creating. I'm creating this heap. The values of this heap. 10. 10's left is 4. 10 centered is 5. 10's right is 7. Is it a max heap? Is it a max heap or not?
Yes.
2. And then 3. But of course, this is not there. But sorry, I've given a wrong drawing. No problem. This is the max heap because it is satisfying the max heap property. Now, first we are inserting 6. Where do you insert 6?
Below 5.
Exactly. Not below 5. Please. There are 3 descendants are there. So this is after this particular, 4. Here it is 6 is inserted. Is it right or wrong? Hello.
But how can we, it should be smaller than the parent, right?
Wait. First, whenever you want to
Okay.
create a
We are
max
just
heap,
filling it.
First it is we are filling at last, then we are trying to heapify. Clear?
Okay, yeah.
So after 6, then we try to heapify. These two are swapped. Is it right?
Yeah, got it.
Now, the heap, it looks like 10, 6, 5, 7, then we have a 2, 3, and 4. Is it clear up to here? Is it clear?
Yes.
Yes, sir.
Now we are inserting 1. So 1 means simply we can insert here. No problem, no? Because no swapping required. Heapify not required. Clear?
Yeah.
Because 1 is below that 5 and 5 is bigger than 1, it is satisfying max heap property, no problem. Next value we are inserting is 12. So when you are inserting 12, again there is a heapify, there is swap is done. One swap is done, what happens? Again one more swap is done. Is it right? 12 will come to top, 6 is here it is 10 is coming, here it is 7 is as it is because heapify works here. So when it comes to this 10, so then after it 6 is okay, no problem. This 6 is having 2, 3 and 4. This 10's left is 1 as it is, it's there, no problem. But here 5 will come. Is it right? Is it right or wrong?
Yes.
Because it is
Swapped.
swapping is done, no? Yeah. So next one 8 is inserted. While you are inserting 8 here, no problem. Is it right?
Yes.
Because 8 is below the 10, no? 10 is a bigger value. It is satisfying max heap property. Now 9 we are inserting. Where do you insert 9? At this place of 7. Is it right? Below the 7, no?
Yes.
So there is heapify is done. So what happens that 12, we got that. We got the 12. Sorry, I'll make a list directly because I don't want to write more. First 12, then 6. So then after it 10, then after it 9. Is it right? Because level by level, no, you are going. Clear? Then after
Yes.
it 2, 3, 4, 1, 5, 8, and then 7. Please check it. Which one is right answer? 12, 5, 10, this is okay. Up to 9 is okay. 3 and 4 is also okay. 1 and 5 and 8 and 7. So this is the right option. Please check it. It is satisfying that whatever heap it is created. Okay. Already existing heap. We are inserting the heap elements. Whenever it's required, heapify you are doing. That's like bottom up. Okay. It's straightforward. Nothing great we are doing. Is it clear?
Yes, sir, it is.
Yeah.
Yes,
So
sir.
because it is heaps are definitely it should be a complete binary tree, then we process for that. So now one more question is given. So this is so question number 8. Consider a max heap. Already max heap is there. It is built repeatedly into the empty heap. Suppose the last value inserted was 95. Maybe last value inserted. What was the heap structure before the value is inserted? Let me consider this heap we are creating. I'm trying to create that heap. So that how the heap it looks like is, your existing heap it looks like is 70. See, it's a binary heap. It's not 3-array heap because previous one is the 3-array heap. Now it is a binary heap. Binary heap means only left and right is there. 43, 47, and then we have 24, 47, then after it 12, then after it 31, then after it 39. Is it right? I think this is the heap it is by using the above list. Is it right? Hello?
Yeah.
Yes.
Now,
Yes.
now, what could be that heap if the 95 is the last inserted element? Before inserting, what could be your heap it looks like? Can anybody give you the idea of that? Very easy, straightforward question. Before, if it is 95 is the recently last inserted element. Recently last inserted element is 95. But before inserting 95, how your tree it looks like? How your heap it looks like?
Sir, I think 70 will be at the top.
Yeah, it's okay, but how can you easily trace out that? Maybe this list, how can you trace out for that? So very simple. We try to do that. Always heap-5 we do that bottom up, no? We try to do that reverse order. Reverse order means this 95 will come to you this way. Is it right? Because it
Yes.
is
Yeah.
this path only, possibility of this particular heap-5 is only this path. Am I right or wrong? Because
Yes,
the
sir.
last element 95 might be inserted here. So in that time there is a heap-5 is worked. So before heap-5 it looks like what happens, 95 will come to here, so that 70 will come here, 95 will come here. So 95 again swapped with 47. Maybe here it is 70, here it is 47, here it is 39, here it is 95. Is it right?
Yes.
Now your heap, it looks like 70, 47, 61, and then it is 43, 39, sorry, it is 24, 47. Only we have to do that reverse CP5 path. If you draw the reverse CP5 path, you can get it. 43, and this is 12, and this is 31. So we got that 70, 47, these three options. Out of these three options, 61. This is okay, 61, we got it. After that 43, after that 43 means this. After that 43, 39. So 39, 43, 39. Yeah, wait. Okay, this is right. Then after that 24, 47, 12, and so this is the right answer. The right answer is B. It is correctly matched. Only we do. Generally, we do the heap-5 in this way. We do the reverse heap-5 because the top element we are bringing to the heap-5 path, which is a log path, what you can call, so which is the possible paths where the possible heap-5 is happening. That's top to bottom, not like bottom up. So this is one interesting question. Maybe I'll get back to the mock, don't worry. Yeah, this is one more interesting question. See, there is a min heap. The min heap is already created. I hope you know that min heap property is what? What is the min heap property?
Maximum to minimum, like
Exactly. So
the root
minimum
node is minimum.
Root is always minimum. Then it's left and right descendants. So that it is a 10, 25, 45. We have 35 and 38. It is satisfying the heap property, which is min heap property. 70, 54, and 43, 39. Okay, that's okay. Built repeatedly by inserting the values into the empty heap. This is a heap, it is built. Which of the following value could not have been the last element inserted in the heap? See, out of this heap, just you guess it. What is the last element inserted? Just you blindly guess it. What is the last element may be inserted? What is the last recently inserted element? Hello?
39.
Yes, 39 is definitely the last inserted element. Maybe if not the 39, definitely in this path only it is inserting is possible. Sorry, heap-5 is possible. Is it right? Is it right? If it is not 39, maybe 35. Due to the heap-5, 35 went back. Maybe 25. 25 is heap-5 and it went back. Maybe 10. So 10 has been heap-5 and go to the root. But it's not definitely 38. Am I right or wrong? It's not definitely 38, no. Because we changed the level. We changed the level and we are going that at previous level. So here there is a possibility of 25 inserting as a last element. There is a possibility of 35 inserting as the last element. There is a possibility of 39 as the last element. But there is no possibility of 38 because it is cross. It is not in the path of heap5. Recent heap5 path is not there. Is it right?
Excuse me. Like you said 25 then 35. How can we but heapify 35 and 39? The minimum heap property will be spoiled, no?
Maybe recently inserted is 35. Already 39 is there. Heap5 might be happened, no?
Like, but 35 is smaller than 39. How can we do it?
Min heap, no? It's a min heap you are talking about.
Yeah, so
No,
30.
You're talking about min heap property satisfied or not min heap property. How it is satisfied? Whether heap5 is done. Is it right? So that maybe 35 is inserted first, 39 is inserted means no heap5 required. Clear?
Okay.
If it is 35 is inserted after 39, maybe heap5 is done. But heap5 is possible only in this path. Is it right?
Yeah,
Because
38 cannot go there. Yeah.
So always heap5 is possible on the last leaf. Is it right? Is possible on last leaf. Who is the last leaf in the entire tree? This one, no? Clear?
Yeah, got it.
For example,
38 cannot jump this side, yeah.
Yes, this side it cannot. If, for example, the tree is closed here, so this is heap5 path. Is it right? Sorry.
Now
so,
it can go. Without 38, 9 and 43, it can.
Exactly. So if, for example, the tree is 10, 25, something like 45, and then what is 35, 38. Then what is the last node?
38.
So that heap5 is possible only in this path. Is it right?
Yeah.
That is. What is the last node is there? From that last node, try to draw a heap5 and try to identify which of them are allowed, which of them not allowed, which is going cross.
So the elements that can be swapped basically.
Exactly. The possibility of swapping, but 38 there is no possibility because it is out of order.
Yes. Okay. Thank you.
So, okay, maybe I don't want to go for the binary search tree directly. Just let me go for this similar kind of questions. See, there is a sixth question, maybe. Yeah, it's okay. There is a binary tree with 20 nodes, where that number of children with two children is, 2 children, 1 children is there, no, that's what they are talking about. If a particular binary tree is there, there might be a chance of 2 children is there. It is 7. The total number of nodes with 1 children will be. So this is somewhat interesting question. Maybe there is a constant and a standard formula. Maybe I'm going with here itself. So here, so n is nothing but n is nothing but this n is nothing but number of nodes with 0 children, number of nodes with 1 children, number of nodes with 2 children. Am I right or wrong? Is it right?
Yes.
How many nodes we are finding means that the kind of node we are trying to find out in the binary tree. A tree nodes with 2 children, a tree node with 1 children, a tree node with no children. No children is called leaf. So here already 20 is given. The 20 is given. So that the n is already given 20. Whenever 20 is there, the edges are going to be 90 because it's a binary tree. So it is just connected, not a complete, or we can say that it is. So in this, they are already given n2 value. N2 value already given, no? N2 value is already given 7. Is it right?
Yes.
Now there is a constant formula. So how to find out the n0 is n2 plus 1. This is the constant how to find out the number of leaves in a binary tree. You can take anyone. So for example, I'm taking This is a binary tree. Now, my N2 value is 1 because number of nodes with 2 children is 1. Then my N0 value is, N0 value is 2. Is it right?
Okay, so N0 is basically leaf nodes.
Yeah, N2 plus 1. Simply.
Yeah.
So even you go with another bigger tree, something like this. Something like this. So here, N2 we got it, 1, 2, 3. Is it right? N2 is 1, 2, 3. 3 nodes are there, no? 2 children.
Yes.
The nodes with 2 children. Now N0 is nothing but N2 plus 1, that is 4. So these 4 are going to be leaves. Up to this is clear?
Yeah, clear.
Now, in this particular N equal to N0 plus N1 plus N2, already we got this N2 value is 7. Okay. Now N0 value is definitely 8. Because what we say that
N2 plus 1, yeah.
N2 plus 1, which is a constant kind of calculation. What we can do is a binary tree property. Now, what is remaining? What is remaining at this place? To equalize this 20, to balance this, definitely it's going to be 5, no? Is it right or wrong? Yeah, bring it to one side.
Yeah.
So that my N1 value, the number of nodes with 1 children is going to be that definitely 5. The right answer is here 5. So please remember, this is the constant formula. This is a constant proved one. A binary tree, when it is having the 2 children, so a node with 2 children is N2. So N0 value is definitely N2 plus 1. So what is my N is already given 20. So N2 value was given. Using N2, we can find out N0. So the difference between N2 and N0 and what is the remaining is the N1, which is making balancing with N value, which is 20. So we got the.
Is there anything for like this formula for N1 as well?
No, it is reversing of it. If N1 exclusively you want to find out it, this is the only way. Bring it to N1 one side. What is that? If it is doing plus means what should I do that? Bringing to one side, it's going to be minus 1.
Okay.
Clear? That's simple. That is equal balance. What is left to right moving operators we and make it something
I mean, if like few values are missing, like suppose 7 would not in that.
No. One of the value must be given, like N0 value, N2 value. They'll give it. So there is similar kind of question, I think so. Just let me check it. This is a different question. Yeah, this is a different question. Yeah. Somebody wants to ask something.
Yeah, sir. This question, can we do it by drawing a tree directly?
Yeah, it is okay, but I don't think
that would be time consuming.
Time consuming, no? So very easily you can. So there is one more question, I think, in this. First, let me finish up this. In this, one more question was given, like similar kind of question. So first, let us finish the question number 10. Is it okay? Hello.
Yeah.
Yes.
So here, the binary tree traversal, there are 3 order of traversals are there. Just I'm recollecting what are the different traversal of binary tree. There is in order traversal is there. Just I'm recollecting the concept. So in order means left, root, right. Is it right? Hello? In order traversal. Whenever a binary tree is there, that first traversal of in order. Do you know that in order traversal? Traversing all the left nodes, then root node, then right node. Is it right? Hello?
Yes, sir.
So next one is pre-order is there. Pre-order means first root, then left, then right. So that's called pre. First we are root, we are traversing. And the next one is that post order. Post order means left, right, and root. So please remember here. Now the question is the following binary set tree is that the letters indicates the name of the nodes, not the values that are stored. Simply The values are not given, just only that letters indicates that, you know, alphabet, something like that. What is the predecessor node in terms of the value of the M? Predecessor, I will tell you what exactly the predecessor is. So BST, just you recollect it. What is BST? Binary search tree means there is a property for binary search tree. What is the binary search tree property? Can anybody tell them?
Left, sir.
Left is always less than the root. Right is always greater than the root.
root. Yes.
Yes. So that, for example, if the values, it looks like this: 5, 3, 11. See that left of the 5 is less than the 5. Right of the 5 is greater than the 5. Is it clear? Is it clear?
Yes.
Now, the BST in-order traversal, why do you use this? You know, the in-order traversal is first traverse left, then traverse root, then traverse right. So in this way, if you go, the sorted list we are getting. Is it right or wrong? Is it right?
Right.
Because first we are finishing the left, then we are finishing the root, then we are finishing the right, means definitely you will get that list is in ascending order. Is it clear?
Yes, sir.
Hello. Now, predecessor is we are thinking about. See, predecessor and successor. For example, in order, definitely you might have a chance of predecessor and successor. Predecessor means who is before this right, root. Who is after this L, definitely root. Is it right? So this R, right, who is the predecessor? Before the R, which is the root. Predecessor means what? Before, no?
Yes, sir.
Is it clear? So successor means who is after. For example, who is after 3 means 5. So that in order means there is a possibility of predecessor and successor. For example, pre-order you are taking, always possibility of successor only. Generally, we don't search for that predecessor. Post-order means always we check for the predecessor. But right now, in-order traversal, why they ask about is, it is a binary search tree. Binary search tree means the property it is left, root, right. That only it will return that ascending order of list. Now, what is that predecessor node of M? So before M, what is traversed? Before M, what is traversed? That is called predecessor. Now let us consider we are traversing this list in order traversal. In order traversal means left, root, right. Now, A, is it traversed A or is it going for left? What it is traversing first? Is it traversing A or is it going to the B? Hello?
Sir, left first.
Left. So is it B is traversed or it is going to the left?
Sir, D.
Yes. Is it going for the left or traversing D? It's going for still left, no?
Yes, sir.
But after H there, it is a left. So H is traversed first. Is it right?
Yes.
Is it right? First
Yes,
H
sir.
is traversed, no? After H is traversed, then D is traversed because left is over, root is traversed. This is left. This is root. After root is over, again it is going to the right. But this is a root. This is a root, no? Somebody?
Yes, sir.
It's a root of somebody. So
Then
again
go to
left is traversed. So that it is completing O. After that I is traversed.
Then P.
After that P is traversed. This part is over. This part is over. Now, again we are coming to this root. So now B is traversed. After B is traversed, this is a root. We don't traverse it. Then we finish up this left. Then we finish up this right. So that after B is finished, E is not traversed. J is traversed. After J is traversed, E is traversed. After E is traversed, K is traversed.
Yeah.
After K is traversed, this part is over. Completely over. Is it right?
Yes, sir.
Then A is traversed. After this root is over, then you are coming to here. It's a root. We don't traverse this.
It's go to the left.
Yes, left we are going. Again, it is root to somebody. Again, we are going to this. This is a left, complete left. So after A, we are traversing L.
Then
After
F.
that, F. After that, C. Is it right?
Yes.
After C, this is a route. We don't traverse it. We traverse this left. So that M. After M, G is traversed. After G, N is traversed. So now, what is the prior node traversed before M?
Before M, C, sir.
C. So that is called predecessor. So predecessor and successor, if they are asking in the BST, means definitely you need to traverse that using in order. Why do you use in order is because in order only will return that ascending order of list. Is it clear?
Sir, in case of successor and predecessor,
Even successor, they will ask it you also in the binary search tree. You're supposed to go for in order only.
Okay.
Because they clearly mentioned it is a following binary tree. Sorry, binary search tree. The properties.
Yes, sir.
So always binary search tree is mainly used for. Of course, if it is balanced, again balancing factor is different. That is AVL. Let us assume my binary search tree is balanced. When it is balanced, the searching property is going to be always it is log n. Clear? Always it is going to one side only, no? Clear?
Yes, sir.
So at the same time, when you are trying to pick out the elements, definitely simple kind of going to the left, root and right, you will get that list of elements are sorted. Is it clear?
Yes, sir.
Yeah. So give me a 2 seconds. Just I'll get back to you very soon. Just I'll pick up soon. Yeah. So this is one interesting question. Still there is, hello, am I audible?
Yes, sir.
Good. So now again, the previous example like N0, N1, N2, still you are having similar kind of question. Remember, they clearly said it's a strictly binary tree. See, remember, there is a binary search tree. Every node has either 0 or 2 children. They don't have a chance of that having that a tree node with 1 children. For example, we don't have the tree like this. This kind of tree is not there because this is N0, this is N2, this is N1, this is N0. Am I right or wrong? Hello?
Right, sir.
Yes,
Only
sir.
we complete or nothing.
Because we are having that either 0 or 2. That means only this way. You have to fill it. We don't have a chance of only leaving this hole. It must be filled. So that kind of binary search tree is already there. Referred as strictly binary tree. So such tree is having 21 leaves. Already leaves are given. Already leaves are given. So as I said, so already they are having the 21 leaves. So as I said, leaves are, N0, which is going to be 21. Now, the standard formula, whenever strictly binary tree is there, there is another standard formula is there. How to find out the number of nodes is number of nodes they are asking that. How many number of nodes they are, because the fill in the blank, they want to fill it with number of nodes. So the number of nodes we want to find out is very simple. 2 into N0 minus 1. So what is this n0 is? It's a number of leaves. So already we got that number of leaves at 21. So 2 into 21 minus 1. So this it's going to be, you know, 41. 41. Still you want to prove it? This is what the best example. For example, in this n0 is 4. Is it right? In this case, n0 is 4, no? Is it right?
Yeah.
Now, total number of nodes you want to find out means 2 into 4 minus 1. What is this? 7, no?
It is 7. Yes, sir.
So this is 1, 2, 3, 4, 5, 6. This is one more formula. What exactly, you know? They will give only the leaves. They still say that it is a strictly binary tree. Strictly binary tree means either 0 or 2 children is there. We try to find out it. Simply we can do that by using the formula is that 2 into n0 minus 1. Please make sure this n0 is subscript of it, that is number of nodes. So the right answer is exactly having this 41.
So 2 into n0 means 2 into number of leaves.
Number of leaves. N0 means the number of leaves.
Okay.
Okay. Because it's a strictly binary tree. They don't have a chance of having more than one. What you can say that a node with one child. A node with one child is not there. Either 0 child or 2 child. So the last question. Yeah, it is the last question in this, but yeah. So yeah, it is okay. No problem. Visible. Yeah. See the maximum minimum number of nodes. So this is very simple. Earlier, you know the height of the tree. Let's assume that height of the tree is. So as per the Professor Mathavan delivery of lectures, and earlier we have discussed about the height of the tree is, any tree, it is not having any root is height is 0. If at least one root is there, the height is considered as a 1. Is it right?
Right.
Is it right? So when it is going for the next level, the height is increased. The height is increased. So at this time, the height is going to be the 2. Height is going to be 3. Height is going to be. So remember that the height of this, you know, how the tree is considered. Empty tree height is 0, but root is existed means 1. So again, next level we are going. So consider that the height of the tree is 7. So consider the height of the empty tree is that what is the maximum and minimum? Maximum possible and minimum possible. It's a straightforward. So maximum possible we want to find out is very simple. So 2 to the power of h.
Only balanced tree.
Yes. So let's assume it is a balance. So if it is balanced, then what you can say that, you know, complete BST. So it is a maximum. It is a maximum. So what is minimum is just h. Sorry, what you can say that, you know, left skewed or right skewed. What you can say that left skewed. For example, they already given 7. No, if 7 means 7 nodes are there, left skewed or right skewed. Is it right? It is a minimum.
Yes.
So when it is balanced, it is maximum we go where 2 to the power of h minus 1. So h is already given 7, no? 2 to the power of 7 minus 1. So I think it is about 127. Is it right? Hello?
Yes, sir.
So that 127 and 7. So this is the right answer. The right answer is D. Because already height is given 7. So whenever height is given 7, it's a left skewed or right skewed is the minimum one. So 2 to the power of h minus 1 is the maximum. It's a straightforward formula. Consider that empty tree is 0. At least one root is there means it is a 1. Height is 1. When it's going to the next level, the height is increased. It's a straightforward. I don't think it is required much time. So now still the mock questions are there which belongs to that week 5. Let's assume. Yes. For week 5 and 6. Yes. There is 7th question. There is, you know, BFS they are taking. Do you know BFS? Breadth first search. it's a level-wise traversal. Is it right? If it is BFS, you consider the BFS.
Yes, sir. Level wise travels.
We try to traverse this level, and then we go to the next level. That is called BFS.
Level wise travels.
Level-wise traversal. If it is depth, we are going that depth-wise. Then we come back to backtracking. That's different because BFS will use the Q as a data structure background of it.
Yes.
So that's clear. Now let's see that. The question is, yeah. So breadth first search is performed on a binary tree beginning from the root vertex. The root vertex we have started from the breadth first search. Let the distance of a node represent that number of edges from the root. Yes, exactly. For example, we have a root. Maybe your particular tree, it looks like this. Your tree, it looks like this. Maybe it looks like this. We have started from the root. What is the distance from this root? Maybe the distance is representing that number of edges. So let's consider this is a V. No, this is a V. This is a U. Is my screen visible?
Yes, sir.
Hello. How much distance from this root to U to V is edge number 1, 2, 3, and 4. Is it right?
Yeah. Yes.
Yes. So if a vertex or a node V is at the distance of 4 from the root. From the root, actually, I've used a different name, no problem. U, let's consider this is the root, and this is a V. Because as per that question, if a node V at a distance of 4 from the root, that is the last visited vertex. So whenever a distance of 4 means it's going to the last visited of BFS. Then the maximum possible number of nodes in the binary search tree. So here again same formula, maximum possible. So here again the height, it comes to the category. So what is height of this? If you consider this, if the distance they have given is 4, like 1, 2, 3, because distance is already given is 4. Because already 4 edges we are traversing. No. What is the height of this?
5.
What is the height of this?
5, sir.
Yes. 3. So simply, very simple. Height of the particular distance, distance is given. Height you want to find out is the distance plus 1 is simple. So that height is going to be 5. So now maximum possibility you want to find out means 2 to the power of 5 minus 1. So how much is that? It's a 31, no?
31.
Is it clear? So maximum possibility is the 31. So here the right answer is 31. Because already distance is given. If distance is not given, you're supposed to put it first height, height 2, height 3, height 4, height 5. Always distance plus 1 is the height. Because already distance is given, simply we try to find it plus 1. Plus 1 we got it means 2 to the power of h minus 1. Simply go over a calculation is over. So that is a straightforward, but a different way they ask you. That's it. Simple. So shall I go for the next question?
Sure, sir.
Yeah. Now, so again the maxi question. See, a priority queue. So priority queue is nothing but maximum value is at the top, because priority queue is maximum value is processed first. So initially max heap, it looks like 20, 18, 15, 13, 12. The new elements 10 and is inserted in the max heap. The max heap after the insertion of the job. See, already heap is there. 20, 18 and 15. Whether heapify is working or not, it makes a difference. 13 and 12. Now first element inserting is 10. Where do you insert it? Here we are inserting. When you insert 10, we don't need any heapify. Am I right? Because 10 is below 15, no? Is it clear? So, but whenever you are inserting 17, there is a heapify is done. When heapify is done, so we'll have a 20, 18, 17. So
But
then
why,
after
sir? It is correct. No, it is greater than the root node.
root node is 15, no?
Yeah.
17 you are inserting, you have to heapify. You need to heapify or not? You need to insert 17 below the 15. Is it satisfying heapify? It's not satisfying max heap property, no?
No, sir.
So that 20, 18, 17, then 13, 12, then 10, then 15 after heapify. So we got that 20, 18, 17, and after the 13, this is the right choice. The right choice is D. So, yeah,
We make swap, na, sir?
Yeah, we must have swap it for the insert. Sorry. For inserting of 10, we don't need any swap.
Yes.
Because it is max heap property satisfying. But inserting of 17, we need to swap with 17 and 15. So the right choice is D. 15 is going in the last. So here the same question, what I said earlier is same thing. Nothing else. Yeah. I think this question is already we solved it because same pattern of questions. So that is about all these. But 7th and 8th weeks are AVL trees, and this is Huffman coding. All these are in the next Friday we are discussing. But thing is, one more time I'm telling you, whatever questions we have discussed is that more conceptual level and somewhat complex. But most of the times you are getting is pretty straightforward questions like 2 to the power of h minus 1 calculation.
Yes, sir.
So, and similar way, the recurrence relation, sometimes, you know, one more thing I want to tell you, quiz 2 is not based on that 5, 6, 7, 8 units. We have that 1 to 8 units weightage is there. But 1 to 4 weeks, some few questions will come.
Okay. Majority of that major portion is 5 to 8.
Yes, exactly. But you have that sufficient questions from week 1, 2, 3, 4. Then more questions from week 5 to 8. So somebody thought it is only week 5 to 8. If I prepared, that's enough. No, please kindly see that revision session of that quiz 1, if possible. And then you can see the quiz 2 first revision session, and coming up Friday session, we have another session of week 7 and 8. Hopefully we have solved that plot. I did not submit it because maybe, you know, sometimes I submit after that second quiz revision is over. So hope it is clear.
So next revision is on Friday, right?
Friday. Because
sir,
Sunday you have.
I want some suggestion because I want to some practice on the question type of recursion question, sir.
Recursion relation.
Finding the time complexity of the recursion relations by the substitution method.
Because that is divide and conquer policy, there are recurrence relations are there. Is it right?
Yes, sir.
So recurrence relations, they are, you know, the root is dominating child. So I think you can find out that 3 different kind of relations they have given. Root is dominating child, and like recurrence relation tree is there. There are 3 different.
One is the substitution method. By the mathematically we find the time complexity to that. Sir, I want
exactly.
Yes, sir. Practice more question on that because I'm very confusing in that.
So definitely in the 8th week revision, actually in the Friday we will discuss about the recurrence trees only. Recursion trees actually.
Yes, sir. Try to make more question on that substitution methods.
Definitely.
Okay, sir.
I think there is a particular question is there. I think one question is.
Yes, sir. One last question, sir.
Yes. Wait. There are 2 functions are given.
Yes, sir.
So
here it is.
Yes, sir. This type of.
While we are discussing this question, we try to take some more examples also. No worries. Because the mock questions are there. That questions we take on the recursion relations, recursion trees, we build it, and we try to show where the log n will come, where it is n square
Yes,
will
sir.
come, that way.
That is some sequence relations comes on that, sir. We have to put and memorize that thing, sir.
Sure, definitely simple calculus, no problem. It is standard kind of thing. Yeah, Vaikunth, you want to ask something?
Sir,
Hello.
one request. Can you teach week, sir? Can you teach
Hello?
week 6? Can you hear me, sir?
Okay, tell me, Vaikunth.
Yeah, can you teach week 6 concepts only, sir?
No, that you can see that YouTube streamed week 6 completely. So week 6 is, I think there is binary trees, heaps. I think if you want it, I can send you the YouTube link if you want it. Just a minute. Complete week 6. Huh? Just please be online.
Okay, sir.
Yeah, just recent, I think app dev, for it is PDSA, week 6. Huh? Week 6. Summary. Good. Yes, it is 2 weeks ago only. It's an open session of week 6. Right. Yeah, it is just 2 hours session. Actually, quickly you can play whatever the concepts you wanted. Just I'm pasting in your chat box. Kindly
Sure,
preserve
sir.
it some. Yeah, preserve
Thank
it
you.
somewhere. Yeah, there it is having that week 6 concepts of binary trees, heaps. So that min heaps and max heaps and heap sort, all these are put together in single. Okay. Hello. Yeah.
Yes, sir.
Yes.
Yeah, okay, sir.
Okay, then I think we can close the session.
Yes, sir. Very helpful, sir.
So please, please don't miss it in the Friday session. Also, we can have a plenty of questions to discuss. Okay, then
Yes.
bye. Have a nice day.
Good night, sir.
Thank you, sir.
Good night. Good night, everybody.
Thank you.
Thank you, sir.